All right, hello everyone. So we're going to continue with our organic chemistry studies by introducing yet another functional group, this time aldehydes and ketones. And we're going to play sort of the same game that we've been doing. Here's a new functional group. We're going to first learn how to name it. We're going to learn the properties of it, so specifically like boiling point. And then we're going to learn a few reactions of aldehydes and ketones. So first, let's just introduce these two functional groups. They're very closely related. They're almost like one functional group, but we do sort of divide them into two categories. To be honest, it drives me nuts that the chemistry gods did this. I think that they should be considered one functional group, but I'm not in charge. First of all, the most famous sort of example outside of the chemistry lab that you would have heard about an aldehyde or ketone are specifically formaldehyde, which is the simplest, smallest aldehyde that exists, is commonly used to preserve biological species, as well as dead bodies in like a mortuary or something like that. Okay, so let's sort of like focus in here on what we're talking about. Aldehydes and ketones revolve around what's called a carbonyl group, or a carbon that's double bonded to an oxygen. So the bond itself, this guy right here, we call a carbonyl. Okay. That's like the name of the bond. And again, that's a carbon double bonded to an oxygen. An aldehyde is when on one side, or two, but at least one side, there's a hydrogen. Okay, so that carbonyl carbon is bound to at least one hydrogen. That's what makes it an aldehyde. Or if the carbonyl carbon is bound to two carbons on either side, that's what makes it a ketone. Okay, so the only difference between an aldehyde and a ketone is in an aldehyde, the carbonyl carbon is bound to at least one hydrogen. In a ketone, the carbonyl carbon is bound to a carbon on either side. And because, this sort of goes back to similar sort of bond geometry that we were talking about when we were talking about alkenes, and how those bonds are in a trigonal planar formation. And so the angle between all those bonds is 120 degrees. So this central carbon here, all of these bonds are 120 degrees, right? With alkanes, we said they formed a tetrahedral type shape. With alkenes, because of that double bond, they form a trigonal planar shape. And that's the same thing with aldehydes and ketones. They have a double bond in there, so it's going to be forming a trigonal planar shape. That carbonyl group has this certain property called polarity, where the oxygen has a partial negative charge on it, and the carbon has a partial positive charge on it. Okay, so this carbonyl group is polar. So that's going to mean that when it's present in our ketones and aldehydes, that's a polar group that's present in in both of those functional groups. Okay, so in terms of naming, and we'll talk about properties about boiling point and solubility and all that good stuff in the next lecture. This lecture, the main focus is going to be naming these different functional groups. We're going to start off with aldehydes. They're a little bit easier because, so first of all, when we have our aldehydes, we'll use the ending al, as opposed to like alcohols, remember, we're OL. Aldehydes are AL. And one of the things that makes aldehydes really nice is because they have to be located on a terminal carbon, right, on the end of a molecule, because of the fact that there has to be that hydrogen bound to that carbonyl carbon. So because of that, we don't need to worry about numbering our parent chain, because it's always going to be at the end. It's always going to be at carbon 1 is going to be where that aldehyde functional group is. And then, these smaller ones especially are commonly referred to by common names, but I don't want you guys to be bogged down with memorizing all of that stuff. I know the Iupac names are tough enough as it is, so I'm trying to limit what I think is the most important parts of this chapter. So there are common names. If you want to be really good, you can go ahead and have those memorized. That's great. But for me in my exam, what I really care about are these Iupac names. And so let's worry about getting those here. So first of all, let's just go in on our simplest one here. Right, we have 1 carbon, so we keep that meth prefix. And then there's only single bonds, so it's methan. And then we have that al suffix because it's a aldehyde, right? Same with ethanal. Again, now we have our 2 carbons. So that's our eth prefix. We have 3 carbons, that would be the prop prefix, and again that al suffix, propanal. And 4 carbons would be butanal, right? So but being 4, and again that suffix al. 5 carbons, pentanal. 6 carbons, hexanal, et cetera, right? And again, I don't have to include the number of where this functional group is located because it's always going to be on the end. So it's always going to be on carbon 1. Right, so that kind of makes it a little bit easier. We have another sort of special benzene or aromatic aldehyde that we're going to have to just know the name of, and that is Benz Aldehyde, right? When we were talking about alcohols, we had something similar. We had the aromatic alcohol was called phenol. It had its own special name. Same thing with the Benz Aldehyde, the aromatic aldehyde that we're going to talk about. So that just has its own special name. You'll have to have that known as well. Okay, so how do we go about naming an aldehyde from scratch? We really just apply all the same rules that we have before, but with our new suffix that we have. So step 1, as always, is find the parent chain, that largest continuous set of carbons. So 1, 2, 3, 4, 5. I have, in this case, a 5 carbon parent chain. I'm going to start numbering. And again, the thing about the aldehydes is that aldehyde group always gets carbon 1. That's why we don't have to number it, because we know that we're going to put it at carbon 1. But when that means that you have substituents and all that good stuff that you got to keep track of, make sure that you're numbering starting at that carbonyl carbon. 1, 2, 3, 4, 5. Identify our substituents. So I have a methyl substituent here, and it's located at carbon 3. So this is 3-methyl pentanal, right? My 5 carbons tells me I'll have this pent in there, and then my aldehyde functional groups gets me that al suffix. Okay, for ketones. We add the -one suffix. So this would be propanone. Okay. Acetone is probably the most commonly used common name in all of organic chemistry that supersedes the Iupac. Acetone is the common name for propanone. That is a really good one to know. In terms of, I know I say that you guys don't have to memorize common names and all that good stuff. Acetone is just one that is really good to know because it is even more widely used everywhere than the Iupac name. But anyway, so we're going to, with aldehyde, or with ketones rather, distinguish it with the suffix -one. Okay. We, again, sort of just to go through, right, we have our 3 carbon ketone, 1, 2, 3, so that would be propanone. Again, that ONE suffix, the prop, because we have 3 of those. Again, you can should know the common name for this one is acetone. Besides that, I'm not going to make you memorize common names for aldehydes and ketones, but again, acetone is just an important one. What about when we have one, two, three, four carbons for our ketone? That would be butanone. And again, we got that -one suffix. When we have 1, 2, 3, 4, 5 carbons, that would be pentanone. And then notice here that because it's a ketone and not an aldehyde, we do have to indicate that this our functional group is located on carbon 1, 2, 3. So this is 3-pentanone. Okay, we didn't have to do that with butanone or propanone because there would have been no other way to draw this molecule that would have been anything other than, for example, 2-butanone. You would have been tempted to say 2-butanone to identify that location, but there's no 3-butanone, right? It can't be 1-butanone because that wouldn't be a ketone, it would be an aldehyde. So the only butanone that exists is this 2-butanone, and so we just let it be as butanone. Kind of like the same reason why we don't, for ethanol, we don't say 1-ethanol, well, because there's no such thing as 2-ethanol, right? Same thing with propanone and butanone. When we get past 4 carbons, pentanone, hexanone, heptanone, octanone, all that good stuff, you do have to specify the location of the ketone. Because, for example, given down here was 3-pentanone, well, there's also 2-pentanone, right? So at that point, because it's no longer unambiguous, we have to specify the location of that functional group. So again, this would be 2-pentanone, 1, 2, 3, 4, 5. I have the pent because of my 5-carbon parent chain, and then the -one because it's a ketone. When you have cyclic ketones, they're pretty easy to name. You just stick cyclo on the beginning, just like kind of with what we normally do, right? So cyclopentane is what it would be if it didn't have this ketone functional group. That'd be cyclopentane. And then as soon as we stick that ketone on there, it becomes cyclopentanone. All right. And similar to why we don't have to do this for most of our cyclic compounds, we don't have to indicate that it's at position 1 because it's always going to be at position 1, right? If we moved it to another carbon, we would just renumber such that that carbon is considered position 1. So it's cyclopentanone, not 1-cyclopentanone. When we have other substituents, then we do have to indicate their position because we're going to start numbering at that ketone group. So 1, 2, 3. So this would be 3-methyl, right? And the 3-methyl is my substituent here. We have cyclohexanone, cyclohex, because it's a 6-membered ring. 1, 2, 3, 4, 5, 6. And then again, how we name our ketones is with that -one ending. Right, so let's go about the Iupac name for this compound here. Again, what's our first step? Same first step as always, find that parent chain. In this case, 1, 2, 3, 4, 5. This is our longest continuous set. And then you're going to number in such a way that gives the ketone the lowest possible number. Right? So a ketone functional group, kind of like the alcohol's functional group or the alkene functional group, are special in that, you know, let's number it both ways. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So previously when we learned we want to use the smallest number possible. Well, in both of these numbering schemes, I have a 2. But again, just like an alcohol group or an alkene group, the ketone sort of takes priority in that it's going to be the one that gets the lowest number. I'm not even going to pay attention to the methyl group when I'm picking between the red or the blue numbering scheme. All I'm going to pay attention to is what number does that ketone have, and I want to make sure it has the lowest number. So in this case, it's the blue numbering scheme that's correct. So I'm going to get rid of the red here. And so this one would be 4-methyl 2-pentanone, right? I had to specify the location of that ketone group. So 4-methyl, that's because I have a methyl group on carbon 4, and then the 2-pentanone comes from the fact that that ketone, that own group, is located at carbon 2. And of course, that pent comes from the fact that I have a 5-carbon parent chain. Okay, yeah, so as we said, formaldehyde, which is the common name for methanal, the smallest possible aldehyde, is very famous for being widely used to preserve biological specimen. It turns out that biological tissue, like the ones that we have, can last basically just forever if it's preserved in formaldehyde. It really like freezes it in place. It's not terribly good for you. It's incredibly volatile, meaning if you were around formaldehyde, it stinks really badly, and it actually irritates your nostrils and everything like that. So yeah, it's not really good for you, but does do a great job at preserving biological tissue. Ketones, so that's a famous use for aldehyde. The famous ketone would be acetone. And that is just sort of widely used as, I think probably the most common usage would be in nail polish remover, are almost always acetone based. But yeah, it's also used in things like rubber cement and cleaning fluids. The solution that you use to get paint off, yeah, those all contain acetone. It's mainly used as a solvent. It's really good at dissolving other stuff that water does not dissolve. It's actually also a key intermediate in a lot of our body's metabolic cycles. If you were to drink a bottle of acetone, it would be very toxic, very not good for you. But our body, your cells do produce small quantities of it as intermediates in reactions. And then the Benz aldehydes are actually very pleasantly smelling compounds. They've got some famous flavoring kind of neighbors. So Benz Aldehyde is actually got a very almondy kind of smell and flavor. The key component of vanilla is Benz Aldehyde, and same with cinnamon. The key component is kind of not, I guess, not a Benz Aldehyde in the sense that it doesn't have this exact group there, but in the sense that it's a aromatic aldehyde. So you still have that benzene ring in that aldehyde group. Okay, so if we're going to identify ketones and aldehydes, one thing, these first two are actually really good examples because I personally don't use condensed structures a ton. I'm a bond line kind of structure guy, but it is important to be able to recognize these types of formulas in their condensed structure. So this CHO, this is an aldehyde. All right, so in terms of like the signature of an aldehyde, that's CHO. And if you think about it, if we're going to sort of expand this out, let me move this over. Sort of always remember how many bonds carbon can have, right? So currently what's drawn is carbon has this bond to the previous carbon. There's a hydrogen on there, and then an oxygen. Well, that oxygen can't just be single bond oxygen because carbon needs 4 bonds. So that's how you know it's a double bond oxygen. Same with the signature for our ketone is, you see this CO in the middle of the chain. And again, you just want to think we have our carbon where 2 bonds are explicitly drawn. Those are those 2 here. And then you have an oxygen. Well, it can't just be an oxygen with a single bond because carbon needs 4 bonds. So that's how you know that that oxygen is double bonded and is a ketone. Okay, when they're drawn out like this, at least for me, it's a little bit easier to see this. The way that we are going to tell, though, if we're going to like sort of do this the long way, step by step, we're going to identify that carbonyl carbon and then look on either side, right? So this is a carbon and this is a carbon on either side of my carbonyl carbon. So that means that this is going to be a ketone. Do the same game down here. We're going to identify our carbonyl carbon and look on either side. Over here we have a carbon, but here we have a hydrogen. That makes this an aldehyde. Okay, let's go through and do some Iupac names again. First you got to identify whether you're talking about a ketone or an aldehyde, because that will tell you whether you're going to use the al ending or the -one ending. So for this one, again, I've got my signature aldehyde, CHO. Then I got to identify my parent chain, the longest continuous set of carbons. I'm going to start numbering. And again, remember, I'm always going to start numbering from that carbonyl carbon, from that group that contains that aldehyde. So 1, 2, 3, 4, 5. So this will be a pentanal. And specifically, I have a chlorine located at carbon 4. So this would be 4-chloro pentanal. Again, I don't have to say 1 pentanal because it's an aldehyde. It's always going to be on carbon 1. Okay, for this one, I have now our special aromatic aldehyde, Benz Aldehyde. Okay, so that's sort of going to be the parent chain of my compound here, is the Benz aldehyde. And then I'm going to start numbering, again, always numbering with number 1 at that group, that aldehyde group. So 2, on carbon 2, I have a 2-carbon substituent. So this would be 2-ethyl benzaldehyde, and that's all one word. So let me smush this together better. 2-ethyl benzaldehyde.